Uh, Good morning, everyone. Welcome to the lecture of the material science. Right, so today is the last day of our lecture, and I'm very sad. I cannot see you anymore. But just in case, if you fail this course, you are very welcome to come again. I will see you next year. Okay? Right, okay, so I just have one announcement to make. On the coming Friday will be the celebration of our learning, right? The last chance is the last chance for the celebration of our learning, which is the final exam on coming Friday. Start from the 8 o'clock until 10 o'clock. So good luck and best wishes for you. Okay, so take the exam well, and you won't see me anymore. Okay, uh, so today, as usual, we are going to have a quick recall about what we have learned in the previous day, previous lecture, and then we are going to move to the new knowledge, new materials. So last week or on Wednesday, we learned the atomic vibration. Hope you still remember. So the definition of atomic vibration is, these atoms will vibrate, and we call it pulsating lattice. Pulsating lattice means that it's kind of random walk. Random walk means that all the atoms move in different directions, different amplitude, and different frequencies. So that's what we call pulsating lattice. And atomic vibration is related to the temperature. And at the room temperature, generally, the vibration frequency is about 10 to 13 hertz. That means 10 to 13 vibration per time, per 1 second. Okay, so this is the frequency. How about the amplitude? The amplitude is about 0.01 angstrom. We know the size of the diameter is about 1 angstrom, right? Okay, sorry, it's about 10 angstrom. It's about 1 nanometer, 0.5. 0.5. The diameter is 0.5, and 1 is about 1. So it's about 1 out of 100, the size, the distance. Okay, so this is kind of vibrational amplitude. So, and also we know that if we increase the temperature, then the average energy increase. That means what? The vibration will be more violent, right? Will be more quick. So if we drop the temperature down to 0 Kelvin, then there's no vibration at all. Okay. And here is the kind of vibration frequency. Just for your information, you don't need to remember this at all. So it's related to vibration frequency is related to the speed of the sound and the density of the crystal, something like this. Okay. So this is what we learned about the atomic vibration. And after that, we move to the microscope, and we talk about 3 techniques. The first one is TEM, second one is SEM, and third one is the SPM, but we skip the SPM. Today we are going to have a quick look about the SPM. So electron microscopes, including SEM, SEM, or TEM. For the SEM is reflection beam mode. So electron beam hit the object and reflect. So we got the information about the surface of the objects. So as you can see, this is the SEM image. And this scale bar tells you the size of this material. So if from here to here, it's about 2 micrometer. So as you can see, this cube, you don't know what is this. You don't know, but you know it's a cube. They are cubes, right? So you know the size of the cube is about one micrometer, 1 micrometer per one distance, per one axis, right? So it's kind of one micrometer times 1 micrometer times 1 micrometer distance cube, right? So this is the image of SEM. So important information you need to get is the scale bar, and you know the size, or you know the morphology, you know the geometry of this material. The second one is called TEM, transmission electron microscope. Electron beam use the transmission mode to shoot to shoot through the objects. So as you know, for the SEM, you don't know what is this inside. But with the TEM mode, you can see actually there are many pores or many lattices in the cube or in these objects. So you can find out that this is a transmission mode. So as you know, the TEM is more powerful than SEM because you can see the things inside of the object. Okay, right. So this is the information you want to know about SEM. And for the TEM is a kind of interactions between a sharp tip and the surface of a specimen. So this is a sharp tip here, and this is a specimen sample. So you have some interactions between the sharp tip and also the top of the surface. So what kind of interaction? It's all related to the forces, like van der Waals forces, like magnetic forces, like electrical forces, like thermal energies. Okay, even electrochemical forces or electrochemical reactions, something like this. So you can create many type of the prompt microscopes. So this is kind of family. So you can have STM, AFM, LFM, MFM, STHM, and EFM, and so on, NSOM. Right. So there are many types of the scanning prompt microscope. Then that's what we call scanning prompt microscope. Okay. So these are the information we want to know. And today we are going to move to a new section or new chapter, which is called diffusion. You know, from chapter 1 to chapter 5, we are all talking about what we call thermodynamic. Thermodynamic means that it's something to do with the final statement, final states. There's nothing to do with time from the beginning to the end. We all talk about in the beginning of the stage, in the beginning of the phenomena, or in the end of the phenomena. So it's nothing to do with time. This is what we call thermodynamics. And now, today we are going to talk about kinetics. Kinetics is that what we want to know is from the very beginning to the end, and what's going on between the beginning to the end. Okay, so everything to do with time. That's what we call kinetics. So if you are a chemical engineer, there are only two subjects you need to know. Okay, the first subject is called thermodynamics, which is the final stage, and what's the final answer. Okay, this is the thermodynamic, and the second one is called kinetic, chemical kinetics. So it's something to do with time. You want to know at a certain time what's going on at that point. Okay, so today again we are going to talk about diffusion, which is something to do with time. Okay. So this is a gill, right? You know, as you can see, this is a gill. So this gill is a kind of, we call carbon steel. The carbon steel is that inside is iron, but outside we coat a very thin layer of carbon together with iron. So we put the carbon into the iron. And as we know, as we introduce this to you in chapter 4, this is what we call interstitial solid solution. Okay? So this is the end of situation. This is the final products. So how are we going to put the carbon into this gill? And then how long does it take? Can you take about 1 hour or 1 day? So this is kinetics. Okay, so if you enlarge of this area, and you can see there are many small carbon atoms fit between the iron atoms. Okay, but inside there's no carbon. Inside there's no only surface. Okay, so this is what we call, because why carbon can go into the iron, because the size of carbon is smaller than the iron. That's why we call it interstitial, right? So the maximum concentration of the carbon is about 2%. That's what we have learned already. And this technique is called cast hardened steel gill. Okay, so our surface layer was hardened by a high temperature heat treatment. So how can carbon go into this gill? Because we use high temperature. We use the carbon in the gas phase, and carbon diffuse into this gill. So this is a case appeared as a dark outer ring. Okay, so the carbon from the surrounding atmosphere diffuse into the surface. So carbon diffuse into this surface. But you might ask, Professor, I never see carbon in gas phase. Do you know the methane? Methane is CH4, right? Methane is in the gas form. Okay, you know the natural gas, right? 天然气, natural gas contains about 80 to 90% of the methane. It depends on the area or the location you produce the natural gas. But anyway, if you introduce the gas, natural gas into a high temperature chamber, and you put a gill in, so the carbon, the methane will decompose from CH4 become C carbon and hydrogen. So carbon become an atom and deposit on the surface of this gill and diffuse from the surface into the inner of the gill. Okay, so hardness and the resistance can be enhanced. Okay, so there are many types of diffusion. So diffusion is solid state mass transport, okay, by a random atomic motion. So the things you can see the diffusion very often is in a liquid or in a gas. For example, if you want to have a latte, right? You have a coffee, black coffee, and you put a milk into the latte. If you put the milk into this black coffee, and you use your spoon to stir, so this kind of milk diffuse into the coffee, and this eventually this become a latte, right? So this is kind of diffusion, but this is liquid to liquid, right? But today we are going to talk about solid to solid. Okay, so diffusion is the solid state mass transfer by random atomic motion. Okay, a type of the phenomena of the heat treatment. So that means the break bonds. You know, if you have this atom and this atom need to move to this place, this is called diffusion. You need to have a vacancy. If there is no vacancy, there is no diffusion. So this one need to move to here. This one need to break bonds between the adjacent atoms and then form the bonds. So you need to break bonds and form the bonds. That's why you need what? You need energy. And where is the energy from? Thermal energy. So you need to increase the temperature in order to break bond and then to form the bond. Right, so diffusion is related to the temperature and also the time. If you have a increase the temperature, you make the diffusion go through 1 minute and 1 hour, they will tell you the different story. Okay, so and also related to the heating and cooling rate. So materials of all types are often heat treated to improve their properties. Okay, so how are they going to improve their property? As just information tell you that it's called hardening, right? You put the carbon into the iron, and then this steel will call carbon steel. Right. So these are the topics we are going to talk. But unfortunately, I don't have much time to talk about all the topics. So we can just go through the first 3 topics today. So first of all, I will go through this very quick. So section 5.1 introduction, there are 2. I want to introduce you 2 terms. The first one is interdiffusion. The second one is self-diffusion. So diffusion is kind of phenomena that the atom move. It depends on the temperature and time. So the phenomena of the materials transport by atomic motion. So atom move, right? So stepwise migration of the atoms from lattice side to lattice side. So this is lattice side, this is lattice side. So there are 2 types. One is this, we call this is vacancy, right? And this is interstitial. So there's a kind of diffusion demo. I'm sorry, I don't have time today. But anyway, I just want to show you this case. If you have a tube, glass tube with water, and you have ink, you have a drop of ink, and you put it in end of ink. At the time 0, it looks like this. But if you increase the time 1, time 2, time 3, and even time 4 or time infinite, what we call thermodynamic, right? Time infinite, and eventually this ink will distribute in this tube evenly, right? Uniformly, right? So the phenomena of diffusion, there are 2 in terms of solid. The first one is called self-diffusion. Self-diffusion means you have this is vacancy, and this is A atom and B atom. A atom and A atom. So you self-diffusion between this. And second one is interdiffusion or impurity diffusion. Right. So what is self-diffusion? You have the same atom, but you just mark this atom as A atom. You just mark this atom as a B atom, but in fact, they are the same type of atom, like carbon and carbon, iron, copper and copper, the same. So self-diffusion means that this is labeled the atom. So the pure metals, but all the atoms exchanging the positions are of the same types. So if you have vacancy, and you know that this will move before diffusion, after the diffusion, the A atom might move from here to here, from here to here. Okay, so this is what we call self-diffusion. So how about interdiffusion? Interdiffusion means that you have different metals, like copper and nickel. Of course, you need to have a vacancy. So the position here is 100% nickel atom. Here is 100% nickel. So the concentration of copper or nickel looks like this. But after the thermal treatment or heat treatment, and you will see that some of course, you increase the temperature higher, like 500 Celsius or 800 Celsius. The nickel atom will move from right hand side to the left. The copper will move from the left hand side to the right. Of course, you need to have a vacancy, otherwise it doesn't move. Okay, the profile of the concentration will look like this. Okay, at a certain time. But if you go to if you have temperatures infinite, the time is infinite, this will be very even distributed, right? The atoms of the copper and the nickels. Right, so this is interdiffusion. So interdiffusion or impurity diffusion looks like this. So please read this by yourself. Okay, so this is the simulation of the interdiffusion. So you have A type of atom, B type of atom, you have vacancies. Right. So I just introduced you 2 terms. Now let's move to the section 5.2, diffusion mechanics. So diffusion mechanics, again, there are two types. The first one is this vacancy interstitial. So there must be an empty junction site. That's why it can move, right? So the atom must have the sufficient energy to break bonds, and then moved, right, with its neighbors atoms, and then cause some lattice distortion during the displacement. So as we know, this is atomic vibration, and then vibrate. If you have more energy, this vibration will big enough to move to the next position. Okay, so atomic energy is vibrational in nature. So at a specific temperature, some small fraction of these total numbers of atoms is capable of diffusion motion. Okay, and then this fraction increases with the rising temperature, as this all what we all know. So there are two models. As I just told you, the first model is vacancy diffusion, what we call substitutional diffusion, right? And this is called interstitial diffusion. So these are very easy, so please read this by yourself. So vacancy diffusion is that, you have a vacancy. Of course, vacancy, this is the void fraction. The void fraction is related to what? The temperature, right? Activating energy against thermal energy. I hope you still remember. So you have vacancy, and because of the temperature, this one move. So this is vacancy diffusion. The significant concentrations of the vacancies may exist at the elevated temperature. If you increase temperature, you have more vacancy. If you have more vacancy, you will have faster diffusion. So both self-diffusion and the interstitial diffusion occur by its mechanism. So no vacancy, no self-diffusion, and interstitial diffusion. You need to have a vacancy. This is vacancy, right? So interstitial diffusion is that this one moved to here. So the position of the interstitial atoms before diffusion, and this is after diffusion. So you have a space to move. So in the diffusion of impurities such as hydrogen, carbon, nitrogen, oxygen, these are all small size atoms, okay, which had the atoms that small enough to fit into the interstitial position. Okay, so if you do the comparison of these two types of diffusion, this is substitutional diffusion or vacancy diffusion. This is interstitial diffusion. So which one will be fast? This one will be fast, or this one will be fast? Faster. Of course, interstitial, right? Because for this vacancy, you need to have more vacancies. But for the interstitial, there are plenty of space. This atom can move around. So this one, interstitial diffusion, will be more rapidly than the diffusion by vacancy mode, right? Because interstitial atoms are smaller and more mobile. So more empty interstitial position than vacancies. Okay, the probability of the interstitial atomic movements is greater than for vacancy diffusion. Okay, so how are we going to proceed the diffusion, the processing using diffusion? I hope you still remember. How are we going to put arsenic or boron into the silicon? This is what we call what? N-type or P-type? Which one? If you put arsenic into the silicon wafer, and this type of wafer is called N-type wafer semiconductor or P-type semiconductor. N for negative, P for positive. Negative, right? So N-type semiconductor, you have more electrons. You have more electrons, which is what we call negative. So dopant silicon with the phosphorus for the N-type semiconductors. Okay, so this is the image of the surface of a semiconductor. As you know, this is light region is silicon. Light region is silicon. But if you put another phone, the light region is aluminum. So this part is aluminum, right? And surrounding this part is aluminum, this part is silicon. So how are we going to put aluminum into the silicon? Or how are we going to put the arsenic into the silicon? And this is one of the process, which is very old type of process we call diffusion. So deposit the phosphorus-rich layers on the silicon surface. So this is the cross section of the silicon, and then we put this phosphorus on the surface. Like if you put a chemical on your skin, and then that chemical go into your skin. So when you have muscle ache. Yesterday you play basketball, you have muscle ache. Today, and you go to the drugstore, you buy a tab and put the tab on your, and you have muscle ache here, and you put the tab here. So the medicine will penetrate into your skin and go to your muscle and release the stress of your muscle, right? Okay, so you feel better. So this is the way of diffusion. So in terms of the semiconductor, you put the phosphorus on the surface of silicon, and what happened? You heat it. You increase the temperature. So this one doesn't go up. Well, it will go up a little bit, but most of them go in. So this one, as you can see, the layer increase. So the phosphorus diffuse into the silicon. But as a matter of fact, this is not that as simple as this. It required some different techniques. But anyway, this is the way for you to understand of the diffusion. Okay, so as you can see, if we increase the temperature, the phosphorus will go in to the silicon and make this type of silicon become negative N-type. Okay. Right. So just for your information. Right, let's go into the very important topic today. And this will be in your final exam, 100%. Okay, that's section 5.3, steady state diffusion. Steady state means what? It's nothing to do with the time, but the diffusion still continues. Okay, so the first term we want to know is called diffusion flux. Assume you have a plate, which is metal. So diffusion is what? Diffusion is solid state mass transport by random atomic motion. So this is the definition you need to know. And then it's time-dependent process. So it's the function of time. So once you want to create an equation, it's always related with the time. So the first term we want to know is called diffusion flux. We use J to represent diffusion flux. Okay, so J is mass flow rate. It's rate. Okay, how fast diffusion occurs and the rate of the mass transfer. So J is that kind of related with time. So J is something like this. J is equal to mass divided by area and divided by time. Okay? So in a very small moment, and you can use differential equation. So J equal to dm divided by a dt. Okay? So mass is the you can use the mass or the numbers of the atoms diffuse through a perpendicular to the unit cross-section areas of the solid per unit of time. So the unit area and the unit of the time. Okay, so this is the definition of flux. So ladies and gentlemen, please, you need to remember this one. Okay, so Jx left, and then atoms went through from left to the right in solid form, and Jx right. Okay, so this is the flux. So the unit can be kilogram per square meter times time, or atoms per square meter times time. So this is the unit of the area, a unit of the time. So how are you going to calculate the diffusion flux? Very easy, right? How do we quantify the amount of the rate of the diffusion? So it's easy. If you can measure the things from the left and to the right, so measure empirically. So empirically is that make a thin film or membrane of a non-surface area and impose concentration gradients. This is important. You need to have a concentration gradient. That means so that you can have a flux. So the mass diffusion will be, you measure the time from here, and the mass diffused from left to right, and you can do the calculation, right? So J is related to this with the slope. So that's why you can that's how you measure. Okay, and measure how fast atoms or molecules diffuse through the membrane. Or this can be like this, can be like this, can be always 0. Just for you to know that. So the flux can be fluctuated with time. So now today we just only talk about one simple case, which is steady state diffusion. Steady state diffusion is that the flux will be keep a constant. So the flux does not change with time. So this is what we call steady state condition exists. So the material from the left to the right go from the left to the right, it keeps as a constant. So the common example of the steady state is the diffusion of the atoms of a gas through a plate. This is a plate for which the concentration of the diffusion species on both surfaces of the plate are held constant. What does this mean? Steady state diffusion. Steady state diffusion means that I have material which is concentration at left is a constant, and then on the right the concentration is a constant, but the concentration on the left is greater than the concentration at the right. But the flux from this place to here keep as a constant. This is what we call steady state diffusion. Why? So the flux x and flux x to flux x. Why? Because when we talk about diffusion, we always talk about concentration gradient. The force of the diffusion will driven by the concentration gradient. So if you have a greater concentration at the left, the mass will move from left to the right. Vice versa, if you have a concentration greater is great on the right hand side is greater than left hand side, the material will move from the right to the left. Okay. So let's make an example for you to have a better understanding. This is diffusion profiles. We use boron into the wafer. So this is a silicon wafer. Okay, and here is the distance from 0 to distance x. And the boron diffuses into the silicon wafer. So if you put a boron on the surface, the boron will diffuse from the left to the right. This is called diffusion. Of course, we increase the temperature. That's why diffusion occurred. And what is this type? What is this type of semiconductor? Boron is p-type, right? P-type semiconductor. So how are we going to do this? If you want to put the carbon from left to diffuse in the silicon wafer, use what? CH4 or C2H2, ethylene or methane. And if you have a B2H6 in the gas phase and increase the temperature, this boron and hydrogen, the bonding will be broken by the temperature. thermal energy against bonding energy. Thermal energy higher, the bond will be broken, right? So you have a boron and deposit on the surface, and you have hydrogen in the gas phase. And then CS fixed by Hb2H6 concentration. So the concentration in the gas phase we hold as a constant, because we can introduce this a constant concentration of the B2H6 in the gas phase. So we keep this as a constant. So boron start to go in. So CS is a constant. So boron start to go in, right? And C0 is 0. So in the end, that will be 0. So we start to do a diffusion. We start, and then you can see the concentration on the surface. The boron concentration on the surface is the highest. Of course, this is CS, and gradually decrease, right? Because it's like running. Boron is start to run from the surface to the end here. Okay. So this is flux from the left to the right, and you know that the concentration here will be smaller than this one, because this holds as a constant always. Eventually, all the silicon will be filled of the borons, but it takes a long time, probably 1 year, 2 years, or 10 years. But for 10 minutes, the surface will be the boron will go in within 10 minutes, and you can see the profile like this. So this is concentration, y-axis, x-axis is the distance from here. So you can plot the concentration something like this, right? It's high to the end and 0 here. So this is time 1. How about time 2? Time 2 might be like this, right? Time 3, time 4. Okay? So flux is a nonlinear concentration gradient. So with the time going by, and then goes by, and then you will know that the concentration profile changes. However, I hope you still remember when I talk about this when you are in first year. If you have a nonlinear equation, how are you going to make a linear equation in order to make an equation? If you have a nonlinear profile, you need to make it as a linear profile, right? And then you can make mathematical equation. Remember that when you are in first year. So the CS need to change to become the function of the concentration, and this need to make another function as a distance. So you have 2 functions, and if these 2 functions can make equation become a linear, so you can make a mathematical model. This is called modeling. I hope you remember this. Okay, so that's what we are going to do this. But we don't have much time, so we are going to talk about Fick's first law first. Ladies and gentlemen, this is also very important, Fick's first law. So diffusion coefficient, we call diffusivity, and activation energy. So what is Fick's first law? The Fick's first law is that you have a plate, right? The surface area is A, and the thickness of this plate is delta X. And then the concentration at the left-hand side is C1. And concentration on the right-hand side is C2. Okay? And then now you have species. You want to make these atoms flow through or diffuse through these plates. Right? Okay. So the question is how to increase the number of the atoms or molecules per time. You know, time is n over dot. 1 is this. 1 represents a species like carbon or molecule or something like this. Okay, in the right side. So you have a few choices. How are you going to increase the concentration from left to the right? First one, decrease the thickness, right? If you decrease the thickness, that will make it faster because this is kind of resistance for the diffusion. So you decrease the delta X, right? How about increase the concentration? Because C1, if C1 is, you increase concentration in C1, that means what? You have it push, right? Atom will be pushed and faster to go through this plate. So increase the concentration. Second one, a third one, if you want to increase the area, that means you will increase the number of atoms on the right hand side, right? Okay, how about other factors? Like it decrease the size of the atoms, it will work, right? Okay, and you increase the temperature, that will work. And you change the structure of the host from FCC to BCC, for example. And we put this all together, we use a DI, this is called diffusion coefficient, as a factor here. So if you put these four together, you can make an example, you can make an equation like this. Mi over dot, so this is Mi, right? Mi over dot equal to what? Diffusion coefficient is a proportion of diffusion coefficient, and then times what? Delta C. Delta C is minus here. C1, C2. If you have C1, C2, this is higher, this is lower. So you vice versa. This is what? Delta C have a minus here. And then you have A. Is if you increase the area, you can have more atoms, right? Okay, and then divided by what? Delta X. The thinner, the better. The thinner, the better. So you can have an equation like this. And then you rearrange this equation. Make move the A to the left hand side. And it looks like this. And what does this tell you? This is flux. So flux equal to what? Minus D. If you do differential equation, that's dC divided by dx. So this is, ladies and gentlemen, this is Fick's first law. Fick's first law. I want you to remember this equation. Right. So the Fick's first law is the mathematics of the steady state diffusion in a single x direction. So when you think of you only have very simple case, only one direction. However, in the reality, you have three directions, and with time. So you have four dimensions to think of: x, y, z, and time. So you need to make differential equation, right? Even partial differential equation. So Fick's first law, but anyway, now we just take a look of the simple case. The flux is proportional to the concentration gradients. So this is what we know. Flux, right? Direction, concentration, and diffusion coefficient. Right, so this is that, I want to move this quick, run out of our time. And this is, if you take out the diffusion coefficient out, and diffusion coefficient, it will be equal to this one. The D0, E exponential, right? And minus Q divided by RT. As you know, Q is activation energy of diffusion. RT is thermal energy. You might think, well, Professor, I learned KT, not RT. R is what? R is gas constant. The gas constant is Boltzmann constant times Avogadro number. That's it. Okay? So the gas constant is the Boltzmann constant times Avogadro number. That's it. So it's again the energy, thermal energy per 1 mole. Okay, so if you do this, if you use this, if you put the log in both sides, you can plug something like this. Again, you want to find out the activation energy with the time. So this is the reciprocal of the T temperature. So you can write down something like this. So you will be able to find out the activation energy using this equation. Okay. So this is activation energy. And you know, in order to move these atoms to this site, this one need to have a 2. That means this want to break the bonds and activation, atomic vibration and move to here. So you have what? Activation energy. This is activation energy here. Okay? And it depends on frequency of the Debye frequency. You can move, this atom will move, right? Okay? Debye frequency. So you have jumping frequency, and you get this together. So in comparison to the activation energy of vacancy or activation energy of interstitial, and you understand activation energy of interstitial diffusion will be smaller. Why? Because you have more space, and this movement is less. Why? Because the activation energy is related to what? The energy of vacancy formation. Vacancy formation first, plus what? The atom migration energy. Atom migration energy together, that will be this. The intensity will include vacancy formation and the atomic migration, atom migration. However, for the interstitial, there is no atom migration. There is no vacancy formation. You don't need to form the vacancy. So only atom migration. So as you know, the energy of the interstitial diffusion will be smaller than the energy of the substitutional diffusion. And that's why this one, small atom, move faster in terms of diffusion, right? Right, and this is related to melting point. I think I just skipped this. So ladies and gentlemen, this is important, and this will be in your final exam. That's why I want to focus on this now. So as you know, that this is fixed first law. This is fixed first law. And if we take out the diffusion coefficient is related to the activation energy and the time. And the temperature. Right. And if you do the log, if you plug the log, use the log to the times log in the both sides, right and left, you will get a plug like this. X is the reciprocal of temperature. Y is what? The log diffusion coefficient. And you know this is, you can plug this as a log scale or cardinal scale. But you know this is minus 15, 14, 13, 12, right? 11, 10, 9. Okay, and this is temperature, reciprocal temperature. But as you can see here, if I make it easier for you, this is 500, 600, 700 to 2000 Celsius. So the plug here is telling you that diffusivity with the temperature. Okay, so let's first take a look of this temperature from increase from the right to the left. And this increase, diffusivity increase. That means diffusion increase. If this is higher, that means what? The atom goes faster. Okay, so as you know, if we increase the temperature and then diffusivity increase, that means diffusion goes fast. Okay? So, temperature increase, diffusion coefficient increase, diffusion increase. This is the example. All the lines increase, you know, from the right to the left, all increase. That because temperature increase. Right? This is one of example. And if you take a look of this line here, this is hydrogen in iron, BCC iron. You know, iron below 900 Celsius is the structure of the iron is BCC, body center cubic structure, right? So hydrogen in the iron, and increased temperature, hydrogen goes fast to the iron. Okay, and this is called interstitial diffusion. Right. And then you really find out that after 900, the diffusion dropped. Why? Because the crystal structure of the iron changed from BCC to FCC at 900 Celsius. And we understand the APF atomic packing factor is 0.68. That means there are 32% of the vacancy in the iron, right? However, if you go to BCC, the diffusion drop. Why? Because APF is 0.74. There are not much spaces for hydrogen to diffuse. There are only what? 26%, right? So this story tells you if APF increase from BCC to FCC, diffusion decrease. However, if you increase the temperature, again, the diffusion increased. Okay, you need to tell me these two information in your final exam. You have more space, that's why diffusion is higher than the less space. Okay, so, and now let's move to the next comparison. This is hydrogen in the iron. This is carbon in the iron. Why? Diffusion of hydrogen is faster than the diffusion of the carbon in the iron. Why? Because hydrogen is smaller, carbon is bigger. The size of carbon is bigger than the size of the hydrogen. So this is what we call size effect. Okay, at the same temperature, the diffusion of the hydrogen is faster than diffusion of the carbon. Okay, this is called size effect. And again, if you increase the temperature, go up to 900, it dropped. The diffusion dropped. Why? Because the structure effect, right? BCC and FCC. Okay, so let's move to the next comparison. This is carbon to BCC to iron, right? This is iron to iron. This is called substitutional diffusion or self-diffusion, right? So iron to iron. So this is vacancy diffusion, substitutional diffusion, and we already know the interstitial diffusion will be higher than the substitutional diffusion or vacancy diffusion. Why? Because this requires higher energy, right? And you need to create vacancy first. So this is what we, and also this dropped. So this is self-diffusion. The speed of self-diffusion is less than the speed of the interstitial diffusion. So vacancy diffusion is much, much smaller than interstitial diffusion. This is the answer you need to tell me in your final exam, right? This is the answer, this is the answer, answer. Okay, so let's move to the carbon. The final is carbon. Carbon in the graphite. Carbon in graphite is that why why carbon in the graphite is carbon to the carbon, right? It's iron to the iron. Why? This diffusion is much, much slower than iron. Because this is covalent bond. Carbon-carbon is covalent bond, very strong. Iron is metallic bond. That's why the iron to iron and carbon to carbon, the diffusion are different. Right. So this is the question in your final exam. I think 100. Well, I shouldn't say that. I should say about 80 to 100% will be in your final exam. Okay. So please remember this page. You know, I hate to fail you, but if I'm good enough, I'm kind enough to tell you what I'm going to test you. But if you don't appreciate this, I had to fail you anyway. Right. So I think I I don't have time today to talk about the rest of the information to you or knowledge to you, but it's very, it's very interesting to learn. But if you want to learn, and you can see my previous record in the YouTube, I will ask my TA to release this record to you in Chinese. In Chinese, I talk in Chinese. Okay, so you can read this by yourself.